Imagine all the smart devices around us, from fitness trackers to industrial robots. They all relying on sensing the world, but how does the raw electrical signal from a tiny sensor transform into meaningful information that a machine can actually understand and act upon? This transformation is a core concept in embedded systems. An embedded microcontroller processes sensor data by first converting the sensor's analog output into a digital format, then cleaning and scaling that digital data, and finally using it in algorithms to make decisions or control external hardware. This multi-stage process is crucial for extracting useful intelligence from the physical world. The journey typically begins because most real-world phenomena like temperature, pressure, or light are analog, meaning they vary continuously. Microcontrollers, however, operate in the digital domain, understanding only ones and zeros. So, the first critical step is analog to digital conversion, or a DC. An analog to digital converter samples the analog signal at specific intervals and quantizes it, assigning a digital value that approximates the analog input voltage. The resolution of the ADC, often expressed in bits, determines how finely the analog signal is divided, directly impacting the precision of the measurement. Once digitized, the data is rarely perfect. Environmental noise, sensor imperfections, and electrical interference can introduce unwanted fluctuations, which we call noise. To combat this, filtering techniques are applied. A simple moving average filter, for example, calculates the average of several recent samples, effectively smoothing out sudden spikes or dips. More advanced digital filters, like low-pass filters, can be implemented in software to selectively remove high-frequency noise components, ensuring that only the meaningful signal trends are retained for further processing. After filtering, the raw digital values from the analog to digital converter might not directly correspond to standard engineering units like degrees Celsius or meters per second. This is where scaling and calibration come in. The microcontroller applies mathematical transformations, often linear equations derived from calibration data, to convert these raw values into their real-world counterparts. Finally, this now clean, scaled data is fed into the microcontroller's core application algorithms. These algorithms interpret the data, compare it to thresholds, execute control loops, or send information to other systems, ultimately enabling the embedded device to perform its intended function. For effective sensor data processing, engineers focus on several practical aspects. Choosing the right sensor with appropriate range and accuracy for the application is paramount. Thoroughly understanding the sensor's datasheet, including its output characteristics and recommended operating conditions, is also essential. When implementing the analog to digital conversion, selecting an adequate sampling rate, which is how often the sensor data is read, is vital to avoid aliasing and accurately capture dynamic changes. Furthermore, the selection and optimization of digital signal processing algorithms are tailored to the microcontroller's limited computational resources and memory, ensuring real-time performance. One powerful technique sometimes employed is a state estimator like the Kalman filter. While computationally intensive, a Kalman filter can recursively estimate the state of a dynamic system from a series of noisy measurements, producing more accurate and stable data than simple filtering alone. This advanced method highlights the depth of signal processing within embedded systems. The efficiency of the processing pipeline, from the initial analog to digital conversion to the final algorithm execution, directly impacts the system's power consumption and responsiveness, especially critical in battery-operated or real-time applications. Ultimately, the sophisticated processing of sensor data by an embedded microcontroller transforms raw electrical input into reliable, actionable information. This intricate dance between hardware and software enables devices to perceive their environment accurately, react intelligently, and perform their designated tasks with precision and autonomy. Understanding these processing steps is fundamental to designing robust and intelligent embedded systems that seamlessly bridge the physical and digital worlds.